Hello students, this is a very brief presentation on some organic and biological or biochemistry. This is from chapter 24 in your AP Chemistry text. Organic compounds are based on the element carbon. Carbon can be joined together in millions of different ways. That's literally true. There are more than 10 million known organic compounds. We're going to look at some of the simplest ones, especially those that contain only carbon and hydrogen, which are called hydrocarbon. Carbon always forms 4 bonds. You must keep that in mind. Always forms 4 bonds. It's very, very important. If it's attached only to hydrogen, hydrogen can only make 1 bond. So you've got to be able to count up how many carbons and hydrogens you have in order to get a good. The simplest of all the carbon compounds are the alkanes, the ones that have only single bonds between the carbons. If there's at least 1 double bond, we call it an alkene, and if there's at least 1 triple bond, we call it an alkyne. Now, chemically speaking, I'm sure you can see why this would make a difference, but the reason why I want to emphasize this is because it makes a difference in the name. So the ANE ending will always indicate an alkane, single bonds. ENE, at least 1 double bond, and YNE, at least 1 triple bond, if you see that as part of the name. Also, what we're dealing with first are what's called open chain or aliphatic hydrocarbons, meaning that they don't join together to themselves in a ring-like structure. We'll get to those in just a little while. The basic rule is to count the to count the carbons. That will give them a prefix, and then you use the suffix for how they're bonded, ANE, ENE, or YNE. So if there's 1 carbon, it's always meth something. If there's 2 carbons, it's eth. If there's 3, it's prop. And 4 is but. After that, it follows the Greek prefix system, so pent, hex, hept, oct, non, and dec. So if there's only 1 carbon and all the rest the bonds are attached to hydrogen, that would be called methane. If 2 carbons are joined together with a single bond, and all the rest are hydrogens, it's ethane. 3 carbons, singly bonded, propane. 4 carbons, butane. 5 carbons, pentane. You might notice that chemically the formula is for pentane, C5H12. What you basically do is double the carbon number and add 2, and that will give you the hydrogen number for all the anes, the alkanes. Here's a mnemonic to help you remember the first 4 prefixes. Monkeys eat peeled bananas. MEPB, meth, eth, prop, but. And remember, after these first 4, the rest follow the Greek prefix system. This is a picture of methane, the simplest of all organic compounds. It consists of a single carbon with 4 singly bonded hydrogens. Methane, of course, is what we burn in our Bunsen burners. It's what's in your gas stove at home or your gas furnace. It is also known as natural gas. If 2 carbons are singly bonded and surrounded by hydrogens, which are also singly bonded to the carbons, then you have ethane. You'll notice over on the left side of the screen that I've shown 3 different ways to represent this molecule. There's a Lewis diagram, a space-filling model, and the ball and stick model. There are also various other ways that we're going to represent organic compounds. I'm sorry if that causes confusion, but the organic chemistry field is just vast and varied, and so various types of depictions have been created for various situations. Here is a depiction of propane, 3 carbons singly bonded to 8 hydrogens. This is also what is known as cylinder gas, or LP, liquid propane. This is the gas that you use in gas grills and gas stoves in the white tanks that you might have out in your back porch or patio area. 4 carbons in a row create butane. Butane is actually a gas, but with just a little bit of pressure, it changes into a liquid.
and so you might have seen it used for butane lighters. Sometimes the lighters have a little cylinder where you can see the butane on the inside, and as soon as you press the button down and release the pressure, it turns into gas, which can be ignited, and then you can light your candle or your gas grill or whatever. When you draw a Lewis diagram, you often draw the bonds just straight across, making the molecule appear to be linear. But as we learned in the previous chapter, actually the 4 bonds around a carbon would be tetrahedral in shape, and so the bond angle would be approximately 109.5 degrees. So if you really wanted to draw these molecules correctly, they would be zigzag shaped. This slide shows a comparison of the first 10 alkanes with their molar masses versus their melting point and boiling point. And you'll notice that as the molecules get larger, their melting point and their boiling point both increase. You'll also see another column over on the right that says number of structural isomers. We're going to learn about isomers in just a little while, but basically that's the number of different ways you could put together those same parts. So an isomer is a different structure created out of the same basic atoms. This slide is a summary of what I just said, that as organic molecules get larger, they basically have higher melting and boiling points. And you'll see in the first bullet that it says that they possess greater intermolecular forces. So if you haven't learned about IMFs yet, stay tuned. Also, please note that the smaller molecules, because they have low intermolecular forces, tend to be gases at room temperature, whereas the larger ones tend to be liquid at room temperature. Now, you can change whether they're liquid, gas, or solid by applying pressure, releasing pressure, changing temperature, and so forth. And again, we will learn about that in the intermolecular forces chapter. Some organic molecules deserve special consideration, if for no other reason than because you are already familiar with them. The textbook, for example, has some really good stuff about gasoline that you should read. Gasoline is not actually a single molecule, but is a mixture of mostly alkanes with between about 5 and 12 carbons. When you pull up to a fuel pump, you may notice the yellow signs with the big black numbers on them. Those are your octane ratings, and basically what that is a comparison of the fuel value or the energy in that particular mixture compared to isooctane, which has been given a octane rating of 100. And then on the other end of the scale is a 7 straight chain alkane called N-heptane or normal heptane, and that's been assigned an octane number of 0. It's not that it doesn't have any energy, it has just been given the rating of 0, and then comparisons can be made on a scale of 0 to 100. Gasoline is actually obtained from the ground. It's part of the mixture of what we call crude oil or petroleum. Straight run means that's what just came right out of the ground, and it has an octane rating of around 50. Various additives and various methods of purification are applied in huge refineries before it ever reaches the gas pump. Things like toluene, ethanol, MTBE might be added to give the octane rating a little bit of a boost. Back in the old days, it was actually possible to add a chemical called tetraethyl lead, and that raised the octane rating, but we found out that lead floating around in the air from car pollution was not really so good for us, and so nowadays all gasoline is unleaded. You probably never gave that much thought, but when you pull up to the pump, it'll say unleaded gas. There are other products that come from the crude oil, such as asphalt. When the petroleum is distilled, you get something that has a very high boiling point, and that's called bitumen or asphalt. It has up to 36 carbon atoms or more. It's very sticky, it's black, it's highly viscous, and you mix it with sand or gravel or something like that, and that's what they make roads with.
Now, what we just saw were alkanes, where the carbons are bonded singly, but you can have double bonds between carbons. They can make up the 4 bonds, so some of those bonds can be double. If you get a doubly bonded carbon, then that becomes an alkene. It ends in a ene in the name. If you have 2 carbons bonded to each other, that'd be ethane. 3 would be propene, 4 would be butene, 5 would be pentene. Ethene in the old naming system was called ethylene. If it is catalyzed properly, the double bond will break and will join together with all the other ethylene molecules around it, and it will make polyethylene, which is known as plastic. If you look on the bottom of your bottle or container, you may see a triangle with a number in it, and that number indicates how dense the ethylene is, or if another material was used instead of ethylene.
If you have 3 carbons with a pair of them having a double bond, then you can create propene, also known as propylene in the old days. You'll notice that the double bond is on one side of the molecule, but the molecule is 3-dimensional, and so you could flip it over and that molecule actually is the same regardless of where you put that double bond. So there's really only one isomer here. Propene, if catalyzed properly, can make polypropylene. This is a tougher plastic than polyethylene and can be used for things like dishwasher safe containers.
Now here's butene, but as you can see, there are 2 different places where the double bond can go. It does make a difference structurally, and so it has slightly different physical properties, and it also makes a slightly different chemical property set. So we have to give it a different name. The rule is that you name the chain that has the double bond in it with the longest possible number of carbons, so in this case 4, so it's butene, and then you give the number of the double bond the lowest possible number. So the top structure is 1 butene, the bottom structure is 2 butene. Here's pentene, and again, as you can see, there's different isomers possible. We can have 1 pentene or 2 pentene. If you look at the bottom molecule, you might think that's a different molecule, maybe 3 pentene, but you got to remember, molecules are 3-dimensional, so you can count from the other side. You don't always have to go from left to right. So if you count from the right, it's again 2 pentene. It's the same molecule as the one above, just flipped over. So what do you think you might call this compound? 1, 2, 3, 4, 5, so it's pentene. And again, we count from the right, we give it 1 pentene. So this is the molecule that we just saw. Always give the lowest possible number to the double bond, 1 pentene.
See if you can name this molecule. Count the carbons. 1, 2, 3, 4. So that's but. There is a double bond, so that's butene. And where does the double bond begin? Well, either way you count, it's on carbon number 2. That would be the lowest number. So this should be 2-butene.
Hydrocarbon can have more than 1 double bond. Here we see 3. You give them each a name based on their position of carbon, and you give the lowest possible carbon set number. So in other words, if we count from left to right here, we have 1, 2, 3, 6 octene, and we call it octatriene to show that there's 3 double bonds. If you counted from the other end, from the right to the left, it would be 2, 5, 6. We always use the lowest number set, so 2, 3, 6 octatriene. Ethine in the old naming system was called acetylene. This triple bond has a tremendous amount of energy in it, and consequently, if you can break those bonds, you release a lot of energy in a short amount of time. In this particular case, acetylene, if burned, can release so much heat that you can generate temperatures over 3,000 degrees. It is the chemical that is used by us chemistry teachers in our Halloween demonstrations. Whenever we blow up pumpkins, we generate this ethine or acetylene from a reaction between calcium carbide and water. If you drip a little water on calcium carbide, one of the molecules that's created is acetylene, and then we can build it up a little bit, light it, and it makes an explosion. Here's propyne. If you were to move this triple bond over to the right, you would still have the same molecule. It's just flipped around backwards. So this is not a structural isomer. On the other hand, we can put the triple bond on the end or the triple bond in the middle. So that's 1-butyne or 2-butyne. Pentyne, same thing. We can have 1 or 2. Now, just FYI, I've been drawing the carbons and hydrogens all bonded together, but there are other ways to symbolize these organic chemicals. Here is 2-butene. Here is also 2-butene. We just take out some of the bonds. This is called a condensed structure. We can condense it even further and just show the double bond. That's the only one of interest, really. Or we could even reduce it even further and take that double bond out because it's, again, not necessary. If you don't see 2 or 3 hydrogens attached to each carbon, then you know something's going on, like a double bond. In real life, the bond angles are not 180 degrees, but are bent at 109.5, and so you really should show it like this molecule shows the bends. But again, chemists get tired of writing all these letters and stuff, and so they start taking off some of them, like this, or even like this. This little stick drawing right here. Every end represents a carbon, and every bend represents a carbon. So 1, 2, 3, 4, butene with the double bond in the middle, so 2-butene. On the AP test, if you were to be asked to draw one of these molecules, which I doubt, but if you did, I recommend you try to draw in such a way that shows all the hydrogens. Don't use the little stick figures I just showed you. Sometimes it's a very long molecule. You can condense it down by using parentheses that show the repeating unit. So CH2 appears here 1, 2, 3, 4 times. So we draw the CH2 in the middle with a 4 or in parentheses. Now, what we just covered were aliphatic or open chain hydrocarbons, but carbon can bond to itself in a ring-like structure. This would be cyclohexane, 6 carbons in a ring. Here's a different way of showing it. And using a little stick drawing, this is a way of showing cyclohexane. You'll notice the name is still hexane for 6 carbons single bonded, but we add the cyclo prefix. For example, here are a few of the chemicals you may have heard of. Naphthalene is the chemical that makes the awful smell in mothballs, if you've ever smelled that. If you look at the very bottom one, with 5 benzene rings all bound together. This is one of the chemicals that would be found in smoke if you were a smoker. This is the kind of things that you're putting in your lungs, not good for you. Now, as I said, we often can join together other things other than carbon and hydrogen. And so we need to take a look at that for a second. We're going to look at what's called functional groups, things that we can attach to the carbon. And each of these groups will have their own little naming rules that go with them. First, we'll start out with what's called the alkyl groups. These are just more carbons that.
So far, we bonded the carbons together in straight chains or in cycles, but you can also have branches. And so the way that you would name a compound like this is you have to decide which one is the root chain and then name the side chains appropriately. So for example, the root chain has to be the one that gives the longest number of carbons, or if there's a double or triple bond or a cycle, then that gets priority. It has to be included in the root chain. Here we see 1, 2, 3, 4, 5 carbons in a row if you count from left to right and you recognize the bends as being carbon atoms that just aren't being shown. They're in this little stick figure molecule. So the root or parent chain is the longest possible hydrocarbon chain. That means that this would be pentane. It has 2 side branches on it, each of which has 1 carbon in it. Those are singly bonded to 3 hydrogens, so we call that the methyl group. So this will be methyl-methyl or dimethyl pentane. And you have to name where the methyl groups are attached. So one is attached on the second carbon from the left, one is attached on the third carbon from the left. If you go the other direction, the numbers will be 3 and 4. You always give it the lowest possible number combination. So we say 2, 3 dimethyl pentane. Here are a few more examples of side chains. If you have 1 carbon, then it's methyl, 2 would be ethyl, 3 propyl, and 4 butyl. You notice in the side chain in a YL, but you give it the same prefix that matches the alkane system. The chain has to be numbered, so again, you give it the lowest possible number. If you have more than one, then you give it each one of them a designation, even if they're on the same carbon. So if you look at the one on the bottom, it's 2, 2 dimethyl butane. You have to be aware that there are various other naming rules that we're not going to cover, plus some old rules that give some prefixes like iso and sec and tert. That, again, it's just because there's so many different molecules that various naming systems have evolved. I'm going to try my best to keep the molecules fairly simple because that's all you should see in the AP Chemistry course. And we're going to try to follow the International Union of Pure and Applied Chemistry rules, or the IUPAC rules. So here's a summary of some of the IUPAC rules for naming hydrocarbons. First, you look it over and look for any double or triple bonds, and then you can pick out the ending. So we're going to kind of name it in reverse. You find the longest parent carbon chain. If there's a double or triple bond present, then that should be included in the chain. If there's a cyclic structure, then that gets priority over everything else. So the longest chain has to start or stop with the cyclic structure. Rule number 3, you assign numbers to each carbon of the parent chain. For alkanes, the first branch should have the lowest possible number. Alkenes and alkynes, the first carbon of the multiple bond should have the lowest number. And you always number them consecutively. Any kind of attachments or side chains have to have a number, and if there's more than one, then you should also assign a prefix. If you have a cyclic structure, for example, you have to call it cyclo, unless it's a very specific structure like the benzene ring, in which case it might have a special name.
The Determine the correct name for each branch. So alkyl groups, methyl, ethyl, propyl. Attach the names alphabetically. So ethyl comes before methyl, even if the numbers don't come before. That doesn't matter. You don't do it numerically. If there's two or more branches are identical, then you use prefix, di, tri, etc., and you give them all a number, even if it's the same number. When identical groups are on the same carbon, repeat the number, as I just said. So if it's both on the second carbon, that would be 2, 2.
Here's a fairly complicated molecule. Let's see if we can name it. The first thing you have to do is choose the correct ending. We notice that there is a double bond, and so the end of the name should be ENE. This is some sort of alkene. We also have to include that double bond in the parent chain. So even though you could count 7 carbons in a row if you counted single bonds, you have to include the double bond, which means that you can only get a 6-carbon chain. That means that it's hexene, and we're going to put that double bond on the first carbon to give it the lowest possible number, so 1 hexene. Now we have to look for branches, and we have to name where those branches are. We notice that there are 2 single carbon groups and a double carbon group. That means there's an ethyl and 2 methyls. And what you should do is attach the names of the branches alphabetically and number each one appropriately. So 2 ethyl and then 4,4-dimethyl. Instead of saying 4-methyl, we say 4,4-dimethyl, 1 hexene. And I do like to put little dashes between my numbers and my names. I'm not sure that's the official way to do it, but it just makes it more clear to me.
Propene. If you wanted to draw propene, ENE tells you there's a double bond, prop tells you there's 3 carbons, might look something like that. 2-butene, double bond, 4 carbons, the double bond starts on the second one. 2,4-dimethyl 2-pentene. Well, let's work backwards. ENE, it's got a double bond. Pent, there's 5 carbons in a row. 2 tells me the double bond starts on the second carbon. The 2,4-dimethyl tells me that on the second carbon and fourth carbon, there is another carbon attached on those 2 different atoms, so it might look something like this. 1-butyne, YNE, tells me that it's got a triple bond, and the 1 tells me that it's on this very first carbon. The but tells me there's 4 carbons in a row, so it would look like this. All right, doing the reverse, here are some structures. So what do we call it? On the first one, we have ENE because we got a double bond. 1, 2, 3, 4, 5 is the longest chain. We have 2 side chains, both on the third carbon, so it's 3,3-dimethyl 1-pentene. What about the second one on the right-hand corner? Well, guess what? It's 5 carbons in a row, double bond, first carbon, double bond, 1-pentene, 2 methyl groups, both on the third carbon. It's the exact same molecule. Don't get fooled because they drew it in some sort of weird bent shape. Now the bottom one is a YNE because of the triple bond. 1, 2, 3, 4, 5, 6, 7 is the longest one, so it's heptyne. And if we look at all the various side groups, we have a methyl, an ethyl, and another methyl. No, we just have 1 methyl. 1 methyl and 1 ethyl. The double bond gets precedence, so it's on the second, so it's 2 heptyne. The ethyl is on the methyl is on the 4th, so it's 4 methyl, and the ethyl is on the 5th, so it's 5 ethyl. Now, the functional group that we attach doesn't have to be a carbon group. It can be another type of atom altogether, such as one of the halogens. In that case, the name changes to show which halogen is attached. It's like chloro, bromo, fluoro, or iodo. And if there's more than one of these halogens attached, then you have to name each one. So if we had 2 chlorines, it would be dichloro. If you had 1 chlorine and 1 fluorine, it would be fluorochloro, chlorofluoro. If it's got a benzene ring in it, a lot of times benzene is part of the name, instead of the other naming system. And so this very top one here would be called dibromobenzene. And you arbitrarily, again, try to give it the lowest possible number set. So we'll call that carbon 1 and the other one carbon 3. So it's 1,3-dibromobenzene. If it's got just a single methyl group on the benzene, that chemical has been given a special name. It's called toluene. It's a very common chemical in industry. Here is an interesting toluene derivative. It's got 3 nitrite groups attached to it. This is trinitrotoluene, also known as TNT, the precursor of dynamite. Now we need to look at a little more detail at some of these possible different ways that a formula could be arranged, called isomers.
The term isomer is derived from 2 Greek words, iso meaning same or equal, and mer comes from meros, which meant a share or sharing. So in other words, isomers are things that have the same or a shared chemical formula. Such as shown here, we have 2 structures that both have 4 carbons and 10 hydrogens. These are known as structural isomers. In the top case, we have what we call butane or normal butane, sometimes abbreviated as N-butane. In the bottom case, in the IUPAC naming system, this will be known as methyl propane. In an older naming system, it was often referred to as isobutane. Now, even though they have the same atoms, they are arranged differently, and consequently, they will have some different properties. They might have different melting points, different boiling points, different fuel values, and so forth. And so we have to keep these structural isomers in mind because some will work for one purpose and some will not.
There are many special cases when ordering functional groups. The N always indicates that if you've attached something, you've attached it on the end. Iso means you've attached it somewhere in the middle. For example, here the double bond is on the end, then this will be N-butene. If the double bond's in the middle, in the old naming system, that would be isobutene. We call it 1-butene and 2-butene in the new naming system. Here is another isobutene. We would call it methylpropene. Here is 4 carbons in a row, and believe it or not, it has the same formula, C4H8. This is cyclobutane. And we can even draw this structure. This is cyclopropane with a methyl group, so methyl cyclopropane. All 5 of these have the same formula, C4H8, but 5 different structures, so they're structural isomers. There are special types of isomers, such as stereoisomers, which mean they have the same molecular formula and even the same sequence of bonded atoms, but where you put one particular set of atoms differs in some 3-dimensional orientation and space. For example, there are some molecules that if you attach them in a particular arrangement and then you try to flip it around, you never can make the exact arrangement, and so you can get what's known as a mirror image or an enantiomer. The enantiomers are very important biologically speaking. It's just like your hands. Your left hand and your right hand are mirror images of each other. Even though they both have 4 fingers and 1 thumb, you cannot make them look.
Chemically speaking, it looks like the 2 molecules could operate almost exactly the same, but there are biological reasons why only one version of the molecule will work. And so life on Earth is made up of these left-handed amino acids, and if you ever got exposed to right-handed amino acids, they can actually make you sick or even kill you. Sometimes that has happened in the past when the right-handed amino acids accidentally got put into medications. Before chirality was recognized on a molecular level, researchers had already found that if you pass a polarized light through certain solutions, sometimes the light would either rotate one way or the other. And so we now know that these enantiomers, or chiral molecules, can rotate the light, the plane of light, in what we call a right-handed way, or dextrorotary, or to the left, which we call levorotary. And we can actually use that property to quickly identify which version of the isomer we have in solution. Here we see two molecules that have the same chemical formula. They have the same atoms. They have different arrangements, so they are isomers. But these are not the same kind of reflection isomers that we were just looking at. Instead, we call these diastereomers. What happens here is there's a double bond, which, as you might recall, has a sigma bond and a pi bond. The pi bond consists of overlapping p orbitals. And because of the double bond, and especially the pi bond, it actually has kind of a stiff structure. And so it matters which side of the double bond you attach something. If you put two things on the same side of the double bond, we call that cis. If you put them on opposite sides, we call that trans.
Here, for example, are all singly bonded carbons. This makes no difference the way I draw it. If I put the Cl up and the Cl down, it's the same as drawing both Cl's up or both Cl's down, because the single bond there can twist any old way it wants to. If I throw a double bond or something like a cyclic structure in there, now it's relatively inflexible. Now it makes a difference which side I stick these methyl groups on. Both of these are 1,2-dimethylcyclopentane, but the one on the left has the same side methyl, that's called cis, and the one on the right, they are on opposite sides of the plane, and so that's called trans. This is another way to represent cis versus trans. In this case, these would be dichloropentanes. So cis 1,2-dichloropentane, trans 1,2-dichloropentane. They have slightly different physical properties, slightly different chemical properties, but like I said, can make a big difference biologically speaking. Here's a double bond, relatively inflexible, so this will be dichloroethene. This is also dichloroethene. The one on the left would be cis, the one on the right would be trans.